My name is Masoud Olia, and I'm a faculty in School of Engineering here at Wentworth, and I'm back again with another video related to kinematics of particles. In this case, we have a particle, a projectile, that is given an initial velocity of 100 meters per second. And the goal is that so at some time, so let's say at t equal 3, right, we want to find the radius of curvature of the path. Now, radius of curvature, as you probably know, is denoted by rho. So rho at t equal 3. So actually, I'm going to show you two ways that you could do this. One would be using this equation. You guys know that the normal acceleration is equal to v squared over rho, or centripetal acceleration. So therefore, if you look for rho, or rearrange the equation, you could change that to v squared over an and solve for the radius of curvature. Now, you might say that, well, wait a minute, I don't have enough information. All I have is the initial speed of 100 meters per second. So how am I going to do this? It's such a little amount of information. So the way this works, remember, this is a projectile. So what we need to determine, obviously, is the velocity at this time, right? And what is the normal acceleration at that time? And I'll show you how you can find those. Well, velocity is obvious, guys. You have your equations, right, which is for velocity. At any instant, you need to find the x component. Now, the x component is equal to v0x always, the initial x component, because we are neglecting the friction in the x direction. So basically, we are saying the only acceleration we have is due to gravity. All right, and then the y component can be determined as constant acceleration due to gravity, right, in the y direction. So we need to obviously go ahead and find the initial x component of velocity, which is v0x here. That would be 100 cosine 30, right, which is 86.6 meters per second. And then y component of initial velocity, which would be 100 sine 30, and that happens to be 50 meters per second. Okay, so now let's go ahead and find this. So Vx is V0x, so that's 86.6 meters per second. Vy would be then V0y, which is 50, right, minus 9.81 times 3. So if you do the calculation here, I have a piece of paper here with me, so I don't have to waste your time and use my calculator to do this calculation. So it turns out that that y component happens to be 20, a little bit more than 20.57 meters per second. So now if you have the x component, which is 86.6, right, like that, and the y component, which is about a fourth of that. So this would be your velocity at that instant. Obviously, velocity is going to be less than 100 meters per second, less than the initial. So that becomes what? Let's go ahead and calculate that. It's a square root of what? 86.6 squared plus 20.57. Now this comes out to be about 89, a little bit more than 89, in fact. So here we go. 89 meters per second is the velocity at that instant. Basically, by looking at the y component of velocity at t equals 3 seconds, that tells us that the projectile is on its way up. So it's still somewhere here, hasn't reached the peak. So see, this is the velocity which is tangent to the path. This is the velocity that I got here, 89 meters per second. All right, so we got the velocity. What about normal acceleration? This is the one that you have to be careful. Remember, at any instant, the acceleration of the projectile, remember it's projectile, it's not being controlled. It's controlled by gravity. is always g. So acceleration is always g at any instant, including at t equals 3 seconds, right? So now the question is, how much of that 9.81 total acceleration belongs to tangential axis and how much belongs to normal axis? This is not difficult, guys, to do. Look, if you realize that the velocity is along the t-axis, or t-axis is tangent to the path, just like velocity. And you see, this is, let me remove this for a second. Then normal axis is like that, and the center of curvature is somewhere here, and what we want to determine is this radius, actually. That's the radius of curvature, right? So then you say, well, look, I know the total acceleration. I can redraw this here for you. So this is the tangential axis, right? This is the normal axis. Now, keep in mind that the total acceleration is gravity. That's g. So how much of this g falls on the normal axis? Well, projected along the normal axis. So this is your an, and well, you can even find a sub t, which would be this. I have no use for a sub t in this problem. So what do I need? I need this angle in a way to figure out what that component is. That angle is the same angle the tangential axis forms with the horizontal x-axis, which is this angle right here, right? And that angle can be determined easily by inverse tan of what? Inverse tan of opposite 20.57, the y component, over what? 86.6. That angle happens to be, I think I'm going out of the frame, so let me put that angle here for you, right here. Theta becomes about 13.36. So now look, guys, this an becomes what? G times cosine of theta. So go ahead, 9.81 g, right? Cosine of the angle that I just calculated for you. And that an happens to be very close actually to gravity because of the angle being so small. 9.544 meters per second squared. So now we go back to our equation here. I can finish it up here for you. Rho equal what? V velocity was what? 89 meters per second squared divided by what? The normal acceleration of 9.544 roughly. And that radius of curvature comes out to be about 830 meters. So that's the radius of curvature at that instant, 830 meters. All right, so this is one way to do it. But you guys probably have seen in my other videos that there is a more mathematical way of getting the radius of curvature. You see, radius of curvature, if you happen to know the equation of the path, and we don't have this equation yet, we're going to get that. If you know the equation of this parabola, radius of curvature can be determined by this equation, which is, as I said, is more mathematical. 1 plus y. See, y is the equation of the path. Y is a function of x. It's the equation of this parabola, right? Not function of time, function of x. So that becomes 1 plus y prime squared raised to power 3/2 divided by y double prime, absolute value of y double prime, evaluated at position x relative to your reference. That gives you the radius of curvature. So now the question is this: how could we get the equation of this parabola, perfect parabola? Because you're neglecting the air resistance. That's why the total acceleration, guys, is what? Vectorially is minus gj. The x component of acceleration basically is 0. That's why the velocity in the x direction never changes. Okay, so let me show you how easy it is actually to find the equation of this path, the equation of this parabola. Once we have this equation, y as a function of x, then we are all set. It's just a bunch of derivatives and plug in. Now, remember, the equation describing the position of the projectile are x equal x0 plus v0 xt based on the constant velocity in the x direction. And in the y direction, which is we are interested to get this equation. But remember, this equation right now is a function of time. So go ahead, plug in. Now x0 and y0, we set it equal to 0 because we can pick our reference right here, right? And so therefore x becomes v0 xt, that's 86.6 t. And y becomes what? v0 y, y0 remember is 0, right? v0 y, 50 times t minus 1/2 of 9.81. Half of 9.81 is 4.905 t squared. Now, remember, I cannot use this equation because it's a function of time. It has to be a function of x, right? So what do? I do a simple substitution. I say, well, look, in this equation, t is what? X over 86.6. I'm going to take that and put it right here and right here. So y becomes 50, x over 86.6 minus 4.905, x over 86.6 squared. And now I'll try to clean this up. Let me see what do I get. According to my calculations here, this becomes 0.5736 x, so that's 50 over 86.6. And then this divided by 86.6 squared becomes a relatively small number. So 0.0030654 roughly. X squared. So now you have the equation. Now you have equation of the parabola. Now you can go ahead and use this formula. So I need the first derivative. That would be 0.57736 minus 2 times that. That would be 0.00, I believe 1308 x. Now the question is, and then let's do the second derivative too, guys. So the second derivative is just minus 0.001308, right? Now, what we want to do is, before we put this in here, let's plug in the x at t equal 3 seconds. So what is the x at t equal 3 seconds? That's the question. Well, here we go. This is your x at t equal 3 seconds. Just put 3 seconds here, and that becomes 259.8 meters. So go ahead, plug in 259.8 here in place of x, and guess what? This becomes, according to this calculation, 0.23754. Now, all we have to do is one last plug-in. Notice that your y double prime is no longer a function of x. So it doesn't matter what x I put in there. So here we go. 1 plus y prime. Y prime was calculated at that x, 0.23754 squared. And remember, the whole thing raised to power 3/2 after you add 1. And notice that you see now why we need the absolute value here, because your second derivative could be negative. Numerator is always positive, but you don't want to have a negative denominator because you want to have a positive rho. Rho represents what? Just radius, distance, right? And this is 830 meters. So 2 ways that we solve this problem. One more mathematical, one based on the centripetal acceleration, an equal v squared over rho, and we got the same results. Okay? So I hope you like this video. As usual, I would appreciate if you like the video and subscribe, and I'll come with more videos using this feature Lightboard, which I really like, and I think you guys like it as well, based on the comments that I have received on YouTube. And we'll come up with more and new examples on different topics, dynamics, statics, mechanics of materials, system dynamics, vibrations, and so on. Again, as always, thank you, and see you soon.